Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content.
I would have seen.
Grade 9s, hello, welcome. Series and parallel circuits is the topic for today. And as you can see, we're going to go through both of these individually. Nothing to specify off them. We're just going to go and dive straight into series circuits first. Series circuit is basically a circuit that its components, so much so, are set up in a series, so they follow after each other. As a bit of an introduction though, in grade 8 we did learn about circuits, and we also learned about the difference between circuits that are in series as well as circuits that are in parallel. Okay, so I think in grade 8, if I'm correct, you could measure the pressure that a specific water pump was supplying to a water circuit. Okay, sometimes a pump or pumping water actually supplies a current, especially as you go more towards the country. Okay, or just a water circuit also as well. There is such a thing as a water circuit. Okay, so I don't know if anybody does remember the diagram, okay, of the water circuit, okay, about how there's a pump and then water flows and then obviously pumps water straight out the system, right? Sometimes out the ground or whatever. A nice little water system to think about would be the windmills. Okay, some windmills are connected so much so that when the wind blows, it pumps water out and then the water flows. Okay, I've seen it on a good couple of movies already, mostly out towards the farms. Okay, so just to explain that again with regards to the water pump, I'm not going to draw the water pump for you because you can always go check your grade 8 book for it, or check your grade 8 textbook, or if you still have that, or simply just go and look online. Since we are online, I'm sure everybody knows how to use the online world. The stronger the pump, the higher the jet of water coming out of the fountain would obviously be. Okay, just explaining that quickly. You could also use a water meter. All our houses have water meters. Okay, in the pipes, you could also measure the amount of water that's flowing through them each minute. Okay, as well as the amount of water that is, you could also measure the amount of water, okay, passing each minute, obviously, through the system. Okay, now, in the same way that I've explained the water pump, or how a water pump works in a water circuit or water system, okay, we can also measure the amount of energy, okay, that is given to the electrons that is carrying the charge in our simple circuit. Okay, and that is measured in volts by a voltmeter. Okay, so let's just take that part down. Okay, if we have a look at what a voltmeter is, which is also another component of a circuit. Okay, now voltmeter is a component of a circuit. It is for series and parallel. And parallel. I know I wrote parallel there, but anyway, it doesn't matter. Okay, so what a voltmeter does, okay, is that it measures the amount of energy that is given to the electrons. Let's see, where's that? Carrying charge. Okay, in a simple circuit or in a circuit. So, to explain, what do you mean by simple circuit? Well, simple circuit would have a battery, okay, a voltmeter, an ammeter, and a resistor and a light bulb. All right, if you want to measure the output. We want to see how current gets converted to light. Sometimes a simple circuit might not even have a light bulb, just a resistor and wires and a switch. Of course, a switch. We need a switch to be able to also control current as well. A switch is good current control. A switch is off, no current flows. A switch is on, current will obviously flow. Cool. So that energy that a voltmeter measured is obviously measured in volts, which we obviously translate to just the capital V. Okay. Cool. And that's everything in a series. Okay, circuit. So like I mentioned, a series circuit, everything follows on from each other. Okay. So to carry on with just explaining also the voltmeter and the volts, whatever, when cells that are supplying the energy, they are connected together in series. Okay, so for a series circuit, when they are connected in series, okay, total energy, this is very important, the total energy is the sum of voltages, okay, of the individual cells. Okay, the sum of the voltages of the individual cells. Okay, so if we look at an AA batteried torch, or a AA torch battery, okay, I'm actually going to go and get mine right now. So let's take this torch battery, for example, a dry cell. Okay, it tells you roughly that it provides about 1.5 volts. Okay, so I'm just going to take this AA battery out. In fact, I also compare a AAA for you right now. Okay, so I've got an AA here, and I've got a AAA as well. I'll just find a loose AAA. I know I had a loose AAA battery, like chilling here, like not so long ago. Here we go. So it tells you on the battery. So I'm looking on the battery now, AAA, and my AA battery also provides about 1.5 volts. This is an Energizer AA battery, and then I've got that was a AAA battery. Now I've got a AA battery, and this AA battery, all right, it's a little different. You just take it out here. This AA battery is a little bit different. This actually provides. Oh no, I'm talking absolute rubbish. No, sorry. This also provides 1.5 volts as well, just as much as this AAA does as well. Yeah, there we go. So an AA battery as well as a AAA battery will provide about 1.5 volts. So my torch at the moment takes about 3 AAA batteries. Sorry, takes about 3 of those, and that can only mean one thing. It's because it needs about 4.5 volts to be powered. So it takes about 3 AAA batteries. Okay, I'm going to put it back inside my torch so I can still have power when I want to use it. Okay, I think this is the right way around. No, it's the wrong way around. Okay, anyway, I digress. Okay, so our batteries that we use in remotes and that we use in our torches or whatever, they provide roughly about 1.5 volts. Okay, cool. Okay, it's off. Cool. It's tripping. Other batteries might supply 6 volts. Okay, cool. It might supply 6 volts. Okay, cool. So now, just as the pressure of the water pump, okay, just as the pressure of a water pump causes the water to flow, okay, it causes the water to flow out of the system or out of the circuit. So the voltage from the cell causes the current, all right, in the wires of the simple circuit. Okay, so we need to add that into our notes here, okay, that the voltage, okay, and I'm going to put in brackets, just like the water pump, okay, causes current in the circuit. So without volts, there can be no current. Okay? Okay, so remember, voltage is the energy supplied, right? So often when they talk even about lightning, they'll say about 9,000 volts or something like that. We'll talk about volts because that's the energy of that electric energy of that electric strike, because that's what lightning is. It's electricity. Okay, so we'll talk about the voltage rather. You'll never say that is a 9,000 amp lightning strike. They'll always talk about the voltage, which is the energy. Okay, so if you have the energy, we can calculate how much current flowed through you, but the volts, that's the energy. Okay, so because voltage actually is what causes current. Okay, so let's read that again. So the voltage from the cell causes the current in the wires of the circuit. Okay, the current remains the same at all points in the circuit unless there is some resistance. Okay, that's a very important point that we need to mention, because this point does not leave the syllabus until grade 12. Okay, is that current remains the same at all points, or we can say throughout the circuit. Remains the same at all points in the circuit. Alright, unless of course there is some resistance, but that goes without saying. Alright. Cool. Whenever an electric current runs through a conductor, okay, whenever there's electric current and it runs through the conductor, okay, there is always some resistance to flow, to the flow of the electrons. Is always. Okay, this is because the electrons are attracted. They are attracted to the positive charges of the nuclei of the atoms on the conductor. Okay, it's something we don't actually need to really take note of for now in this section. Okay, more so when we deal with chemistry in a later on grades, where we actually focus on the nucleus and how there's some type of electrochemical aspect between electricity and chemicals. Okay, and there's forces of attraction and everything. But I'll read that one more time. Okay, whenever an electric current runs through a conductor, there's always a resistance to the flow of electrons. Okay, always. This is because the electrons are attracted to the positive charges of the nuclei of the atoms on the conductor. Okay, so there are electrons on every surface especially of a conductor. So electrons live best on metals. Okay, so sometimes if you touch a metal doorknob or a metal door handle or a trolley at Pick n Pay, and you shock sometimes from static electricity, because that's just electrons that are jumping off onto you, almost like a flea jumping from dog to dog. Okay, evokes almost similar effect. Okay, so a good way to think about this is of a narrower part of a fountain water pipe. Okay, so if you have a water pipe and sometimes water has to go through narrower passages or pathways to pass through the entire system. Even if you take a hose pipe, for example, okay, sometimes we can put a nozzle on the hose pipe and choose the power or the speed at which the water also passes out. Because if we open up the nozzle, all right, a bit wider, then of course the more water can pass through. But if we narrow it a little bit, the less water can pass through. Okay, so think of this when there's some resistance, is that it's the narrower part of the fountain water pipe, and it slows down the flow of water. Okay. Now this is what resistors do. They like that narrower part for water to flow through. Okay. And that part, obviously, in a circuit would be a resistor, which offers some resistance, and resistance would be measured in ohms. Okay, so resistance, if we underline it, obviously resists the flow of current, Okay, and is measured in ohms, which is that little funny symbol over there. Okay. Some substances obviously provide more resistance than others, all right? And in some of these, and in the activities of this little unit that we'll be doing, and throughout grade 9, we often use resistance of light bulbs, as different components in a circuit have resistance. In grade 10, 11, and 12, you will deal with an actual resistor that's only function is to offer resistance in the circuit. Now, to touch on resistance in a series circuit, a resistor with a higher resistance will have a higher voltage running through it. Okay, we need to take that down. Okay, because that logic applies to grade 10, 11, and 12 as well. Okay, why is this the case? If you take a look at our fountain example, our water pump, water fountain example, okay, there has to be more energy to keep the flow of water the same, even when there is some resistance of the pipe. Same thing if you break it down to a little bit more of a homely perspective. Let us take the example of a hose pipe attached to a tap. If you open the tap out at its fastest, or you basically open the tap to its maximum, okay, the resistance that you can obviously add is the resistance on the nozzle, because you can still control how much water is going to go out. Okay, obviously if you open the nozzle full, of course then more water will come out. The water will still come out at the same or at a high speed, but the nozzle will determine how it flows out. Okay, if it flows out like psh, or like psh, okay, obviously, okay, the same thing. So there has to be more energy to keep the flow of water the same when there is resistance of the pipe. Okay, so if there's resistance on the nozzle of a hose pipe, you open that tap a little bit more, okay, that obviously overcomes a little bit of that resistance. There is still some, but it overcomes to obviously keep that water appearing to coming out the same way. Now, on the other hand, if the resistor has a lower resistance, because we mentioned here, we'll have a resistor with a higher resistance, will have a higher voltage running through it. On the other hand, if there is a lower resistance, it will also have a lower voltage across it as well. Okay. Alternatively, it's vice versa also works. Okay. So, higher resistor or a resistor with higher resistance, high voltage as well. Okay. And a resistor with a low resistor will have also a lower voltage passing through it or across it as well. Hope that makes sense for everybody. So to maybe just wrap up everything, I'm just going to draw a basic series circuit. Okay, for everybody. There will be one component that is in parallel, and that is the voltmeter. Voltmeter is always connected in parallel. Okay, so the connecting wire, I'm going to draw the battery. Okay, cool. I'm going to include the switch over here. A little dot and space. Okay, cool. Switch. Okay. There we go. I'll put a key or a legend. A legend's only really used with maps, but anyway, doesn't matter. Okay, I'm not going to include an oh, that's disgusting. I'm not going to include an ammeter here. Okay. But over here, going across here, there's our voltmeter. Okay. So, over here, the key here, this little symbol, this is the bulb, or light bulb. Okay. Obviously, this part here, obviously the battery, and it's a 3-cell battery. because this is 1 part, 2 part, 3 part. Okay. This part here, switch. And of course this part here is obviously the voltmeter. Very simple series circuit. What's in series? The light bulbs. Light bulbs, they are in series. This is what makes it a series circuit. Okay, the light bulbs are in series. When we get to grade 10, 11, and 12, there'll be resistors that are in series and resistors that are in parallel. But we'll see parallel circuits next week. Okay, so don't worry too much about parallel circuits. We'll see them next week. We're going to stick just with series this week. Okay, and that's a basic series circuit, all done and dusted. Thanks so much for joining me in grade 9s, and we will see you next week for parallel circuits.